Hello students, welcome back. Today, we are going to learn one of the most powerful techniques of integration by parts. Have you ever tried calculating the area under a curve where the equation looks like x times cos x or x times e power x? Standard formulas don't work there. That's when this technique comes to our rescue. Let's start from something you already know, the product rule of differentiation. When you differentiate, you multiply it by v. The formula is d by dx of bracket uv bracket equals u into dv by dx plus v into du by dx. That's our starting point. So, integration by parts is nothing but the reverse of this familiar product rule. Keep that thought in mind as we go ahead. Now, let's carefully derive the formula. From the product rule we just recalled, if we integrate both sides, we get uv equals integral of u into dv by dx dx plus integral of v into du by dx. Rearranging terms gives us the famous rule, integral of u dv equals uv minus integral of v du. So the working formula is integral of u dv equals uv minus integral of v du. That's the formula we will use throughout this method. Remember it exactly in this form. Here comes the most important step, choosing which function is u and which part is dv. The golden rule is, choose u as the function that becomes simpler when differentiated. For example, if you have x or log x, differentiating reduces their complexity. And choose dv as the function that is easy to integrate, like e power x, sin x, or cos x. If you choose wrongly, instead of simplifying, you'll end up with an even more complicated integral. And we'll soon see an example of this. Let's put the rule into action with a real example, integral of x cos x dx. Step 1. Take u equal to x, dv equal to cos x dx. Then do equals dx, and v equals sin x. Now apply the formula, integral of x cos x dx equals x into sin x minus integral of sin x dx. We know integral of sin x dx equals minus cos x. So the final answer is x sin x plus cos x plus c. Simple, elegant, and exactly what we needed. Notice how nicely the terms simplified because we chose u equal to x. Now, what if we had chosen wrongly? Suppose we let u equal cos x and dv equal x dx. Then do equals minus sin x dx and v equals x squared by 2. Apply the formula again, integral of x cos x dx equals cos x into x squared by 2 minus integral of x squared by 2 into minus sin x dx. This becomes x squared cos x to plus 1/2 integral of x squared sin x dx. And now the problem is more complicated than what we started with. This shows why the choice of u and dv is not random, it makes all the difference. Let's master this with another famous example, integral of x e power x dx. Choose u equal to x, dv equal to e power x dx. Then do equals dx, and v equals e power x. Apply the rule, integral of x e power x dx equals x e power x minus integral of e power x dx. That gives x e power x minus e power x plus c, or factorized, e power x into bracket x minus 1 bracket plus c. See how beautifully it works? This is the same strategy you can apply for integrals like x sin x or x cos x. So students, let's recap everything we learned about integration by parts. The key formula, integral of u dv equals uv minus integral of v du. Use it whenever the integrand is a product of two functions, especially algebraic with exponential, algebraic with trigonometric, or logarithmic functions. The strategy is, differentiate the algebraic function, integrate the trigonometric or exponential one. And the biggest lesson, choose u and dv wisely, Otherwise, the integral becomes harder. So that's the foundation of integration by parts. In the next video, we'll take this technique further with more challenging examples and applications in definite integrals.